It's getting hot outside. Nowadays, it's difficult to turn on the news without hearing someone talking about global warming. Headlines are filled with references to rising temperature levels, fossil fuels, and encroaching danger. And the discussion around the subject has gotten as heated as the weather. This has been a topic I've been wary about weighing in on, simply because of how sensitive a subject it has become in recent times. I've sat on this particular video for 3 years, occasionally updating it, but not quite feeling it was the right time to release it. I didn't want to simply create more noise. However, I do now think there is something worth adding to the discussion. After all, there is plenty we hear about the current temperature of the planet. What is often not talked about is the patterns of temperature change that existed in the past that contextualize that modern temperature. Are we really the hottest we've ever been? Scientists believe that in the last 100 years, the global temperature has been increasing. But how does this fit into wider patterns and trends? And how did they find any of this out? I'm Alex McColgan, and you're watching Astrum. And today, we will be taking a closer look at the data recording the temperature history of our own planet. It's only by understanding the ancient past that we can contextualize the current discussion on global warming and answer, what exactly are scientists so worried about? So, to begin, how do we know what the temperature used to be? It's easy to find the current global temperature today. All you need is a thermometer, and you can go outside and take a reading. With enough readings taken at different locations around the globe, you can find an average temperature for the whole planet. Scientists have actually been doing this since 1850, meaning that our records on average global temperatures are fairly accurate since this date. However, mercury thermometers were only invented in 1714. So how do we know what the temperature was before these global readings started being taken? How do we know the temperature 1,000 years ago, or even 1,000,000 years ago, before humans were on the scene? Some of you may already know the answer, or at least a partial answer. Scientists can approximate global temperatures in the past through ice coring. Essentially, when snow falls, because it is powdery, it traps little bubbles of air where it lands. If this snow doesn't melt, but has more snowfall on it later, such as in a very cold place like a glacier, you can end up with layers of snow and ice trapped air bubbles going back for many, many years. It creates something similar to the rings on a tree. By collecting ice formed this way, scientists can take sections to a lab and melt it, releasing the air relating to specific years. They then can measure the different ratios of gases released from the air bubbles, which tells them the atmospheric composition at that time. And because we can test how much heat is retained by a gas when exposed to a constant temperature like the sun, for instance CO2 retains more heat while oxygen retains less, with enough samples, scientists can calculate roughly what the global temperature was during that year. However, the oldest glaciers are only 1,000,000 or so years old. To get a good idea of the trends that govern global temperatures, we're going to have to go back much earlier than that. How do we know what the global temperature was over 1,000,000 years ago? The answer might surprise you. Clams. Actually, not clams, but something similar. A tiny single cellular organism no larger than a full stop called foraminifera. Like clams, these organisms produce shells around themselves, and these shells are slightly porous. Oxygen in particular is taken into the shell and trapped there, remaining in place even when the foraminifera dies. So, using a similar process to the ice cores, if scientists can find shells of dead foraminifera from a particular year, they can release that air and work out from it the global temperature. This process is slightly different, as instead of air composition, scientists are looking at different oxygen isotopes, but basically it's a very similar process. Foraminifera are still around today, and first came onto the scene 500 million years ago, so they are instrumental in helping us get a clear picture of global temperatures during this much longer time period. But what is that picture? Based on data collected from Foraminifera, it looks something like this. There is a certain degree of uncertainty to this. Findings get more reliable the closer we get to the present day. But as you can see from general trends, the Earth's temperature has undergone significant changes over the last 500 million years. At times it has faced temperature averages 14 degrees Celsius hotter than we have today, and at other times about -5 degrees Celsius lower. So we are not the hottest we have ever been. Then again, that's not surprising to anyone who knew that the surface of the Earth when it was just formed was mostly magma. But you may not have expected these fluctuations. Why are they happening? Scientists are not entirely sure, as there doesn't seem to be much of a pattern to them on this grand scale, but they believe that some of these fluctuations are from the emergence of new life forms. For instance, the arrival of plants at around 450 million years before the present might explain why the temperature dropped then. They started absorbing atmospheric CO2 and turned it into oxygen, which retains less heat. Other changes could have been caused by plate tectonics and volcanic activity putting more CO2 into the air, and still other changes could have been caused by possible meteor impacts, like the one that wiped out the dinosaurs. However, this is not the full picture. By increasing the resolution and zooming in slightly, we begin to see another interesting trend. Let's look at the 65 million year picture. Within the large sweeping changes, it turns out that there are many smaller fluctuations. These become more obvious when we zoom in again. And again. And again. By this point, we can see a distinct, smaller pattern occurring. Rapid rises in global temperatures, followed by gradual dips. It's hard to get your head around the sheer scope of the Earth's history, but each one of these dips represents entire ice ages. Ice ages are technically defined as any point in Earth's history where there is ice on the polar caps, something that is not always the case. So technically, as I've mentioned in a previous video, we are in an ice age right now. However, although the general trend of the Earth's temperature at the moment is towards ice ages, we are in something known as an interglacial period, a span of many thousands of years where the Earth is temporarily warmer in between full ice ages. In the last full ice age, the polar caps reached the UK and parts of the US. But what is causing these dips and rises on our graph? Well, I go into more detail about this in my video on Milankovitch cycles, which you can watch here, but just to brush up on them very quickly, Milankovitch cycles are the periodic changes that take place within our planet's climate due to fluctuations in its orbital movement around the Sun, usually over the course of thousands of years. Surface ice affects the temperature of a planet. The more surface ice a planet has, the colder the planet tends to be, as more heat is reflected back into space. But equally important is the direction that surface ice is facing. Consider ice to be like a shield that will reflect the sun's rays. If that ice is not pointed in the direction of the sunlight, it cannot reflect it. So anytime the planet points its surface ice towards the sun, the Earth tends to get cooler, creating something of a feedback loop. This matters because the Earth's axis isn't stable. Over the span of thousands of years, it moves back and forth, sometimes pointing the polar ice caps more towards the sun, and sometimes pulling them further away. Although this change is only a couple of degrees at most, it is enough that over time it has an impact on the global temperature. The temperature drops as the ice shield faces the sun and rises again as it points away. This fluctuation is one example of a Milankovitch cycle. There are other Milankovitch cycles, which are consistent cycles in the Earth's orbit that affect its temperature, acting on timescales of 23,000, 41,000, 100,000, 405,000, and 2.4 million years. Whenever these coincide with each other, they create even greater changes to the global temperature. You can see the gaps between the ice ages in this graph tend to be about 100,000 years apart, perfectly in line with one of the Milankovitch cycles, specifically the change in the Earth's orbital eccentricity. But all of the cycles have an impact. So where are we in relation to one of these Milankovitch cycles? Let's zoom in some more. As you can see, we have risen out of an ice age and have entered a fairly stable plateau of global temperature. This is consistent with the rapid rise in temperature / slow drop in temperature that characterizes ice ages and the periods between them. All of human history, from the pyramids to the present day, can be found on this plateau. Although humans existed before this point, they hadn't really got the hang of building any civilizations. Scientists have named this plateau where human history began the Holocene period. However, the uptick right at the end is not so usual. This uptick represents a rise in the global temperature by 1 degree, which technically is still roughly on par with the interglacial period before our current one over 100,000 years ago. However, it is not the temperature change that is concerning about this uptick. It is how quickly it is rising. Unlike all the other changes on all these graphs, which have taken place over hundreds of millions of years at the longest and thousands of years at the shortest, this rise took place in 100 years. This could have a big impact on the ecosystems on the planet. So, what could have caused this uptick? The answer cannot be Milankovitch cycles. As you have seen, these cycles take place on the scale of thousands of years at least, and millions at most. Even when we zoom in on sections of our graph where there appear to be sharp upticks, we realize that these rises take place over a couple of 1,000-year periods. Milankovitch cycles are described as weak but consistent forces, like the trickle of a stream that eventually erodes a mountain. They do not create effects over such a small time frame as 100 years. Similarly, there has been no cataclysmic event such as the one that wiped out the dinosaurs, which might be our other explanation. That meteor was thought to be 10 kilometers wide and struck with a force of 21 to 921 billion Hiroshima A-bombs. About 75% of species died in the climate change that happened in its aftermath. If something like that had hit Earth since 1850, we would have noticed it. However, there is one factor that does explain this change in global temperatures: the activity of humans. It is not the first time that living organisms have had an impact on the global temperature. Remember, it is believed that some of the changes we see here are caused by the introduction of plant life absorbing CO2 and releasing oxygen. Similarly, back when life was still all single-celled organisms about 2.4 billion years ago, the arrival for the first time of cyanobacteria that could photosynthesize had a massive impact on the atmosphere. For the first time, an organism started putting oxygen into the atmosphere. This occurred at such a rate there was an event known as the Great Oxidation Event, which coincided with a significant drop in the global temperature. Some scientists believe the entire world almost froze entirely over, as there is evidence of glacial activity at the equator, a snowball Earth as it came to be known. What we learn from this is that the balance of global temperatures is very delicate. A single species that starts to change the atmospheric ratio of gases can have a massive impact, overloading the subtler effects of Milankovitch cycles. And since 1850, humans have definitely changed the way we have been interacting with the atmosphere. Unlike the previous roughly 10,000 years of human history, since 1760 and the Industrial Revolution, human activity has produced vast amounts of greenhouse gases as a waste product of industrialization and farming. In the last 4 decades, each decade has been the hottest decade on record since we started tracking global temperatures in 1850. CO2 levels are now at a global average of 410 parts per million, and methane at 1,866 parts per billion, which is higher than we have seen in the last 800,000 years, which means since before about 8 ice ages and interglacial periods between them. And importantly, the global cover of surface ice has been retreating consistently since 1950, something scientists do not believe to have happened for the last 2,000 years. As you will recall, this has a knock-on effect on Milankovitch cycles, as a planet with less surface ice does not reflect as much heat from the sun, so tends to get even hotter. Like pushing a cart down a hill, these changes have a certain amount of momentum to them. And sadly, rapid changes in global temperature tends to lead to species going extinct. It normally takes thousands of years for life to adapt to the conditions you might find during an ice age, woolly mammoths, to conditions today, elephants. Natural selection takes time to develop in a species the traits they need to thrive in a new environment. If species are not given this time, they either have to move to a new environment better suited to them, or they will die out. As the habitable zones begin to migrate towards the poles, some zones will vanish completely, while new, hot desert environments will be created that life in general is poorly adapted to. It's important to note that these events are not unstoppable. Global temperature change does have some momentum, but if we as humans find ways to stop changing the atmosphere's ratio, then in time, Milankovitch cycles will take over again and the rise will stop. That's why it's so important for governments to listen to reports by institutions like the IPCC, an international group of scientists funded by multiple governments tasked with finding out the realities of climate change, who in 2021 released their 6th assessment report explaining the physical science basis. In it, they stated that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. However, they also offered suggestions, namely the importance of halting or rapidly reducing CO2 emissions towards net zero, as CO2 is the largest contributor towards climate change, followed by methane. They also recommended the development of carbon dioxide removal facilities to be established worldwide. Some of these are already in operation, such as Project Longship in Norway. Their aim is to take CO2 out of the atmosphere and bury it beneath the ground in depleted fossil fuel reservoirs. The IPCC says that actions like this, if widespread enough, will reduce global surface temperature and even reverse certain other processes like acidification of the oceans. Personally, I'm not super convinced by current carbon capture projects, but they do exist. But these efforts need to be done on a large-scale government level. Ultimately, my aim for this video was to examine what global warming meant within the context of Earth's wider history. From it, we can see that it's not actually accurate to say that we're the hottest we've ever been. And I find that a really fascinating insight. However, that fact alone is not the reason some people think it is to not worry about the problem. Climate change is a process that usually takes millennia. I've realized the worrying part is not necessarily the change itself, but rather the speed at which it is happening. Some life forms might get left behind. And how will humanity cope? We don't know, as we haven't been around long enough to deal with the extremes of the past. While human activity has sped up certain elements, and while we can undo some of what has been done through our actions now, some things, like higher sea levels, will be with us for up to 1,000 years. According to the latest IPCC report, we are past the point of no return for 1.5 degrees Celsius and will need to make rapid, fundamental changes to our society this decade to stop it going any further than that. This will be hard. There's no way we as a species will be able to achieve this hard path unless we can agree on the facts that underpin it though. Without the broader context of agreed upon data, it will forever be perfectly possible to arrive at a wide range of conclusions and different paths we should take. That is why, when it comes to any discussion, context is so important. By looking at the pattern of our planet's history, we see that the current uptick in global temperatures is an induced event that doesn't match already existing patterns, and it perfectly coincides with human activity. Debate what you want to do with that information and the best path to take in light of it, but these are the facts, set in ice and the bones of organisms long dead. They will brook no argument. Dealing with all the crises that the world seems to throw at you daily can get a little overwhelming. Sometimes it's important to take care of yourself. That's why today's video is in paid partnership with BetterHelp. Mental health is a cause that is deeply important to me, and I've seen that when someone is struggling, it can be hard to seek help sometimes. But having someone to talk to, even if it's just to get things off your chest, can be hugely beneficial. BetterHelp is the world's largest therapy service, and they've made it their mission to increase accessibility to that vital service for everyone. Their online platform can get you registered with a credentialed therapist that's right for you in just a few days, giving you access to a wealth of experience as well as that vital listening ear. It's 100% online and remote, meaning you can call your therapist or send messages if that's easier. And if you find the one you're with isn't right for you, you can switch at no additional cost. I think therapy is something everyone can benefit from, and there are countless stories of people who have seen BetterHelp service improve their mental well-being. If BetterHelp is something that you feel could help you, why not support the channel and click my link in the description below, betterhelp.com/Astrum, for a 10% discount off your first month. I highly recommend it. Thanks for watching. Want to learn more about some of the cycles Earth goes through? Check out this playlist here. A big thanks to my patrons and members. If you want to support what I'm doing and have your name added to this list, check the links below. All the best, and see you next time.